Hello, my name is Masanobu Kunitomo. In this talk, I'd like to present our solar models, including the effects of planet formation processes that reproduce the observed neutrino fluxes. Collaborators are Guillot and Guillot Buldgen. On this work, we published a paper last year, and another paper is submitted. First, let me start with a general introduction of star and planet formation. Stars are formed by the accretion from the circumstellar disk, where planets are formed. And the accretion injects entropy and materials, which affect thermal and chemical structure of stars. In a series of papers, we found that the accretion can be crucially important for some observational problems, such as luminosity spreads in clusters, lambda boosters, and chemical peculiarities in solar twins and binaries. And recently, we have focused on this process in the early solar system. Here, I'd like to emphasize two key features of planet formation processes in the early solar system. First, a large amount of solids were used. We estimated that it is about 150 Earth masses, mainly in Jupiter, Saturn, and ejected materials from the outer solar system. This is small compared to the total amount of heavy elements in the sun, which is about 5,000 Earth masses. But still, as I will show later, this is sufficient to affect the chemical structure of the sun. The other key feature is the time variability of planet formation processes. Planets are formed by the coagulation of dust grains. They are initially micron-sized, and once they become centimeter-sized, which are called pebbles, they rapidly fall onto the protosun due to the frictional force with the disk gas. This figure shows the evolution of the metallicity of accreted gas in the literature. The pebble drift increases the metallicity. And once they deplete in the disk or a large protoplanet is formed, the accretion becomes metal poor. So the variable composition of accreting materials is naturally expected. And in this talk, I will discuss how this affects the chemical structure of the sun. We simulated the solar evolution from the protostellar phase to the present day. And the solution at the present day is compared with observational constraints, and we iteratively optimize the solution using the simplex method. As for the abundances, we used low Z composition in Aspirant et al. 2009. And for reference, we also used high Z composition in Grebe's et al. 1998. In this slide, I will show how models are optimized. I will not discuss these results in detail, but instead, I'd like you to see how solutions are changed. This panel shows the total chi-square value, which indicates the quality of the fits to the observational constraints, such as surface abundances, internal structure information from helioseismic observations, and luminosity and effective temperature. The total chi-square value decreases by adjusting these input parameters, and the total chi-square value is minimized. We performed this kind of simulations under a variety of settings, and in this talk, I will show three sets of models: standard solar models, models with opacity increase, and models with opacity increase and planet formation processes, which mean the variable composition of accreting materials. The results will be shown on this panel: boron and beryllium neutrino fluxes at the Earth. Some nuclear reactions emit neutrinos, which tell us the information of the solar central region. And in this talk, I will focus on the boron and the beryllium neutrino fluxes in the PB chain. The green point with arrow bars shows observational constraints. And blue and red squares shows low Z and high Z standard solar models in Vignoles et al. 2017, and triangles shows Farag et al. 2020. This figure shows the observed this figure shows that the observed constraints favor high Z models. On the other hand, recent spectroscopic observations suggest low Z solar surface. So this disagreement is called solar modeling problem or solar abundance problem. We confirmed that we obtain almost the same results as previous studies if we use the same settings. But our standard solar models are different, as shown by the open circles. This is because we used 6 observation constraints. On the other hand, previous studies used only 3. So solution is sensitive to the optimization procedure. And our standard solar model with low Z composition looks good on this panel because it's close to the observation constraints. But I like to emphasize that this model is not sufficient. This panel shows the quality of the fits to the helioseismic and the spectroscopic observations. The total chi-square value of this model is about 3, mainly due to the poor fits to the surface metricity and sound speed. By the way, previous studies used surface metricity, luminosity, and effective temperature as constraints for the optimization. And we added these 3 constraints: surface helium, sound speed profile, and thickness of the convective zone. So standard solar models are not sufficient, and we need additional input physics. Here we consider opacity increase shown by the blue points. The color shows the opacity increase, and the size of these points shows the chi-square value. These big points with 12 to 18% opacity increase have a low chi-square value, less than 0.5, which means that these models reproduce spectroscopic and helioseismic observations very well. However, left panel showed that these models do not reproduce the observed neutrino fluxes. And finally, I will show the models with opacity increase and planet formation processes shown by the star symbols. As you can see, neutrino fluxes are increased and the chi-square value is kept low. So we conclude that the models with planet formation processes and opacity increase reproduce all the observation constraints: neutrino, helioseismic, and surface abundances. So far, I have discussed only boron and the beryllium neutrino fluxes, but other neutrino fluxes like PP, PEP, and the CNO neutrino fluxes are also reproduced within 1.3 sigma. From here, let me discuss why planet formation processes affect neutrino fluxes. This figure shows a metricity profile. The blue line shows a model with planet formation processes, and gray dashed line shows a model without planet formation processes. As you can see, the central metallicity is higher by up to 5%. The higher central metallicity results in the higher central opacity and higher central temperature. And neutrino fluxes are sensitive to the central metallicity and central temperature. So this is a reason why planet formation processes affect neutrino fluxes. The central metallicity is important. So finally, I will discuss how the central metallicity is determined. The red panel shows the central metallicity evolution, and middle and light panel shows the metallicity profile evolution. In the early phase, high Z accretion due to the pebble drift increases the metallicity uniformly in the entire solar interior. The metallicity is increased uniformly in the entire solar interior. And when lossy accretion starts, a radiative core developed. So the central metallicity is preserved. But lossy accretion decreases surface metallicity. And at the end of accretion phase, there's a compositional gradient in the deep interior. This is the accretion signature. After the accretion phase, incomplete Sinono cycle increases central metallicity and develops a convective core. And gravitational settling increases the central metallicity on giga-year timescale. But the accretion signature remains even at present day. So this is the reason why we observe high neutrino fluxes in the model with planet formation processes, and we conclude that planet formation processes should be considered in realistic solar models. This is a summary of this talk. Planet formation processes increase the central metallicity by up to 5%, and the observed neutrino fluxes are reproduced. Thank you very much for your attention.